Okay, now it should be working, right? There is nothing like switching something on for it to work. Sometimes it's not sufficient, but it is necessary. So thank you very much for being here today. I appreciate this. It's a lot for everybody. So this is this lecture, knowing that actually maybe half of the people or even less could make it today. The lecture is being recorded, so it will be posted today for people who cannot come. But I really appreciate the effort that you are putting here, because losing four hours of lecture in the whole quarter is unacceptable. It will give you a disadvantage with respect to the other lectures that actually don't meet on Mondays, right? So it's not possible. It's not acceptable to me, at least, and I hope it will not be. It's not acceptable to you. So, but I appreciate the effort, because this is our third 2-hour session of the week, which is quite a bit for physics, right? Even if you know, even if you like physics. So let us start with a brief review. I usually use my clicker questions for review. We are going to do a small review, and then we are going to go to the clicker questions. So last time we saw Newton's laws. This is what we are going to continue exploring for essentially the rest of the course. And so the first one is the law of inertia. A body continues moving with constant velocity unless acted upon by an external agent. External agent is, in our case, in the case of Newton, a net force. This seems to be many times a subsidiary of the second law. Because you say, well, the net force is equal to mass times acceleration, so, why do I need the first law? Because if I put the net force equal to 0, the acceleration is 0, so I get constant velocity. So why do I need the first law? Because the first law defines the reference frames, the observers, for which the three laws are valid. These laws are not valid in any reference frame. In particular, they are not valid in an accelerated reference frame, right? So the first law says that an isolated body moves with constant velocity. If I am in a reference frame in which an isolated body would appear to be accelerated, this is not a good reference frame. The other laws do not apply. For example, right, if I would be imagine an isolated body. This is really how you can ensure that something is completely isolated. But imagine a body in which there is nothing touching it, and in the middle of nowhere, in the absence of gravity, but I am accelerated. I am an accelerated observer. From my reference frame, this isolated body would be accelerating backwards, right, with respect to me. And therefore, my reference frame is not a good reference frame. As I'm going to explain in a moment, if you really insist in using the second Newton's law in this case, you will have to invent the invisible man or the invisible woman exerting fictitious forces in order to apply these laws with non-physical forces, right? So the second Newton's law is, on the left-hand side, F equal ma, famous F equal ma. What is F? Is the net force, namely the sum, the vector sum of all the external forces to a body acting on it. External forces acting on it. That means that there is only one external force in which you don't see anything in contact, and it is still exerting a force, which is gravity. Besides gravity, that is always there on Earth, it's always there anywhere, but here on Earth, it's always there. All other forces are contact forces. So you will look for, when you are studying a particular body, you will look for contact with others. And each one of those that are in contact with the one you're studying is exerting a force. So those are the physical forces we're going to study. Mass is a scalar, so it doesn't change the direction. So the net force should be always equal in direction to the acceleration, and differs from it in magnitude because of the mass. It's force divided by mass. So now, this law doesn't make sense without the third law. And here we have, I will return back, and I would like, every time you're confused, to think of this example, a simple example to have in mind that you can use as a paradigm to understand what is going on. If you remember, we saw the following, and I will go through this briefly again. Here you have M1, here you have M2. Now I will study M1 plus M2 as a whole body. I can decide which body I use, right? In this case, it's M1 plus M2. So this body, M1 plus M2, here is being pushed. Imagine these are two crates, and I am pushing from here, right? This is a force, F, whose magnitude, assume, is 60 newtons. Remember, 1 newton is 1 kilogram meter per second square, 60 newtons. So N1, let us say, is 20 kilograms. M2 is 10 kilograms. So if I use a diagram, right, we're going to neglect, in the first 2/3 of the course, we're going to neglect the dimensions of the bodies. You're going to consider just that they are a point, they are a particle. So here it is, this force, then we call it push, the force push, F push. And then, of course, there are others. There is a normal force, and there is gravity, which would be M1 plus M2 G. But these two cancel each other, and so the net force is F push. So I know that this body is accelerated in this direction, and the acceleration is 2 meters per second square, right? It's just 60 divided by 30. Are you with me? So both bodies are accelerating, right? This is a given. Now let me consider each one separated, right? I can consider that now, study each one separated from the other. So let me study just M2, okay? I will separate them. So this is for body 2. Well, body 2 is being pushed by body 1, because without body 1 pushing, it wouldn't be moving, right? So again, here there is M1G, and the normal force on this body, these two cancel, because I know, because this body is not accelerated up or down. But there has to be a push here, push off 1 on 2. And I'm going to be very specific. Off 1 on 2. Off 1 on 2. Now you can tell me exactly, using Newton's law, knowing that the acceleration is 2 meters per second and the mass is 10 kilograms, you can tell me what has to be this F net. This is the net force acting on this body. What is this force? It is 20. Exactly. So this is 20 newtons. Now we go to study just body 1. Body 1. So here again, this is a point. Here I will have, oh sorry, this is M2. M2. This is M1G, and it's normal force. I could call this N1, I could call this N2, and this would be N1 plus N2, right? In terms of magnitude, N1, N2, N1 plus N2. In any case, again, these two are cancel each other. These bodies are not accelerated up or down. And here I have the F push. But I know the F push cannot be the net force. I know the net force on this body. What is the net force on this body? The acceleration is 2. The mass is 20. Mass times acceleration is 40. So F net is 60. It means that I need a push backwards in order to get F net. Are you with me? And the only thing that is in contact here is body 2. So body 2 has to be, for consistency, pushing back on body 1, right? So if this is 60 newtons, and I know that the mass 2 times acceleration is 40 newtons, that means that this push has to be the force of 2 on 1. The force of 2 on 1 has to be 20, right? Because 60 minus 20 gives me 40. So I know that this should be the net force on the body 2. So you see that when body 1 acts on body 2 with a force, 1 on 2, 2 acts on 1 with an equal and opposite force. If I wouldn't do that, then I could not split, or I could not consider different bodies interacting together. Now, you can see that actually anything can be splitted into 2 for our study, right? I could split this bottle into 2, consider separately the upper half and the lower half, and I will be in the same situation. So every time I consider a system, the interforces disappear because they come in action-reaction pairs. So this is the third law. Internal forces are not important. You know, we have in our body about 1 billion atoms. They are all interacting. Why can't I just neglect all these interactions to study my motion and consider only external forces? Because all these are interactions, and they cancel out in pairs when I consider the whole system. The same thing when I consider these 2 bodies. Are you with me? So these 3 laws form a logic unity. None of them works without the other. Any questions so far? We're going to continue studying and developing these ideas. Any questions so far? Okay, let us go to clicker questions. Okay, let us test our understanding. Okay, this is the first. So let me start the voting. I don't know why this takes. There. I don't know why it takes so long. I'm not sure if it is syncing or something is in sync with the. So okay, so start voting. This is relatively simple. We saw this actually, this little demonstration at tabletop, right? Something very similar. So this is a path. And then at some point, the body is released, right? So the body, after following that path, has a net force equal to 0. I think we are 66 people today, about half of the people we are usually. Okay, so there it is. Yeah. Okay, so yes. Here is the second. So the question, the right path is B, right? The right path is B. Once it is not being pushed any longer, it will continue with a constant velocity, and therefore in a straight path. So the right is B. Okay, let's say a second one. Okay, now there, I'm sorry, here. These are conceptual questions that don't look beyond simple concepts. I like more Susie, so I think she should be the one that is the strongest, pulling the strongest. Okay, two more. There were 66. Come on, commit yourself. 66. Two people don't want to vote. You have to commit yourself, right? This is a game for yourself. So, okay. So it's both the same y. Who wants to explain this? So the right answer is C. Who wants to explain it?
So with Newton's third law, they're both experiencing the same force going.
That is true. It's also that, so they are not moving right now, so equilibrium will dictate that. But even if they would be accelerated, imagine that the strong man is winning, right? And is dragging poor Susie, screaming and shouting and pouting, right? And it is accelerated. If we find that the rope's mass is negligible, which is of course not zero, but is negligible, then the tension along the string is the same, even if it is accelerated, right? Which is not entirely true, but if the mass is negligible, even the tension, right? So if they are in equilibrium, namely not accelerated, third law. If they are accelerated, if the mass is negligible, then the tension is the same, right? And this is what I put here. The tension is the same along the rope, even if they would be accelerated. Okay. I don't know why this is acting out. I have to really see. Okay, so next one. This one I have the, so please read it, and then we are going to go through this, and then you're going to vote, and then I'm going to show you. So this is what is called the paradox of force. This is another rite of passage. You have the hunter, and everybody does it. There are several problems and several demonstrations that are just everybody. This will unite it with everybody else who is a fellow Physics 1A student. Yes?
So is it like a police system?
This is it, right?
Yeah, so is there one on one side that's on
Right. This is what I'm going to show you. So here, let me see from this side. Yeah, so it is indicated 9.8. So here, let me show you first what this is. This is a scale. So you see that when there is no tension in the string, right, there is no weight pulling on the string, then this shows 0, right? There is a spring here, right? And the extension of the spring is proportional, is calibrated towards the tension of the string, right? So now it's 0, right? So now what I will do is to hang from it this weight, which is, I cannot do it without my right hand, so I will have to do it this way. So I hang it, pass it through here. So now you can see that it indicates the weight. Remember that the weight is mg, and therefore for 1 kilogram is 9.8, or the force of gravity if you want. And this is in equilibrium, so the tension here is equal to the force of gravity because this is not accelerating, right? So it measures 9.8. Can you see that? This is in equilibrium, right? So now I will cover this. I will cover this, but of course this is still the same. It's not that when we are babies that we think that because something is covered it disappeared. This is still there, right? So still there. The measurement is 9.8, right? So now what I will do is to release this from here, right? I release it from here, and I will put here another 1 kilogram. And now I will ask you to vote. Now please vote, right? Which of these 3 measurements is now in this scale? It is 0, because there are 2 forces that are pushing one the other. They cancel out. It is 9.8 as it was before, same as before. Or it is 2 for the 2 kilogram masses, right? This is a conceptual question again. And this is in equilibrium again. All right, so vote. One more, commit yourself, one more. 66, there were 66 a moment ago. One person is not committing. You have to commit. I mean, there is nothing, it's you for yourself, you know? Okay, let us, 67, even more. So down, let us see what you have voted for. So discuss with your neighbor, try to convince your neighbor. This is a very neat question. If you are isolated, please connect, because discuss with each other. You get to know your fellow students. They are your resource. Interact. You can still eat and interact with the people at the back. No problem, right? No, don't remain alone and isolated. Discuss, think, discuss with your neighbor. Try to convince your neighbor, or be convinced. The same thing for you. Try to join them. Look, she is there. Try to discuss with her, please. Right? Yes. I mean, I don't want to be sort of motherly, but I think that you should discuss. Just move and discuss, right? Okay. Let us vote again, because we didn't vote again. Let us vote again. Let us vote again, vote again, vote again, vote again. Vote again, and then we open this up and see what is behind. 8 more people. Come on, come on. 5 more. 3 more. 2 more. There. Come on. 2 more people. I mean, commit yourself. Okay, there are 2 undecided. 2 undecided. Okay, let us see now. Oh! Okay, so this one I think will require the conviction of the proof. Here. What does it read? So how do you think about this? Even before, this was in equilibrium, right? That means that the force on this side, this was not accelerated, right? This is equilibrium. So the tension on this side and the tension on this side had to be the same, right? Because otherwise this would be accelerated sideways. So what is the tension? Here is the force of gravity. This body is again in equilibrium, so the tension has to be equal to the force of gravity, which is mg, right? So what is the tension here? Pushing to the left, your left, is mg, right? What is the force here? Even before, when it was, even before, right? It was in equilibrium. So the tension was mg already. So when I put this body, the tension now is mg again, right? Because this is, in this body I can see, it is the same as this one, it is 9.8 newtons. So this force was already 9.8 newtons. And this is equilibrium, right? This is the concept of equilibrium. So I hope you like that. This is equilibrium, right? So it doesn't matter if you have two. This is the same as before when the string was connected to the support of the scale, because the tension in the string was already mg. So when I put this, it is the tension is what is required to keep this body in equilibrium already, right? Oh, okay. I will repeat this question in different forms again and again. This is a concept of equilibrium, right? Okay, so now let us move to the next one when this decides to work. Okay. Okay. Who wants to explain this? Here, there, at the back. Is anybody who wants to explain this? Anybody wants to explain this answer? Yes?
So, you know that the gravitational acceleration is the same, but force is mass times acceleration, so you have a larger mass and a larger force.
The acceleration is the same. Remember law of falling bodies coming from Galileo Galilei? Near Earth, without air, all bodies fall with the same acceleration due to gravity, constant acceleration, right? Actually, this is true anywhere that the acceleration of gravity is independent of the mass of the body. What is not correct outside Earth is that the acceleration is not constant. It will point, for example, towards the center of the Earth, right? But it is true that the force of gravity is independent of the mass. So the acceleration of gravity is independent of the mass, and therefore the force of gravity is proportional to the mass. So there it is. I think this is the last. No. I have one more for second Newton's law. Let me finish. Okay, this one. Just start voting. Is this a situation of equilibrium? Is this a situation of equilibrium? Everybody? No. Why? Because there is acceleration. Okay, good. Come on, 30 more people to vote. Talk to your neighbor if you want. There is a tendency. Left and right means the left drawing. This is left, and this is right. There are two pictures. One is on the left and one is on the right, in which case the acceleration is greater. But both of them are falling, are moving, are accelerated. But I'm asking in which case the acceleration is larger. Okay. Oh, ha. Discuss with your neighbor. That's one situation in which you really have to discuss with your neighbor. Ah. And then vote again. Try to use this opportunity to discuss with neighbors, right? Don't be isolated. Try to get to know your neighbors. And I'm referring here to you. Try to discuss. Try to get to know some of your neighbors, right? Your neighbors, your fellow students are your resources. Again, just be right. Discuss with your neighbor. Try to convince your neighbors. Come on, vote, vote. 30 more people need to vote, vote. Think of mass and acceleration and force. This is a second law question, right? It's not equilibrium, it's a second law. Net force equal mass times acceleration. Ten more people to vote. Come on, vote. Vote. Commit yourselves. Okay, there are 3 people not voting. Let us see. So let us. This requires then a little bit of thinking, right? Think for a moment. In this case, this is accelerating this way. There is no friction, so this would be accelerating on this way, right? This is falling. Think for a moment. If this is falling in an accelerated fashion, right? Is the tension equal to the force of gravity or not? Is the tension equal? No. It should be greater or smaller? Smaller. Smaller. So when it gets to here, the tension is smaller than this 100 newtons, right? The force of gravity on this body is 100 newtons. So this tension is smaller, right? And this is the same mass as here. So in this case, instead, I'm pulling from the string, right? So the tension in the string is 100 newtons, right? So this body will be accelerating with a larger acceleration. In this case, this is the right, no, this is what, the left or the right? In this case, where the hand is pushing, or in this case? Here the tension is smaller, right, than 100 newtons. Here the tension is 100 newtons. So the acceleration in this case, where the two blocks are alone, should be smaller or equal or larger? Smaller, right? Smaller. So here you have the same external force, more mass, twice the mass. Here you have an external force and you have half the mass, right? Both of them have the same mass. So it is, this one has the smaller acceleration, this one has the largest acceleration, right? Because the tension in the string, in the case of the weight, because they are accelerated, should be smaller. Are you with me? Yeah? Okay, so this is, I think that this is the last, no, this is again a question, simply because it is rather, we have gone through several, again, vote here. We have gone through several similar questions. Come on, this should be easy, because you have answered similar questions before, right? Come on, 6 more. Oh, wow. So we now know that the net force gives you the acceleration, right? So before, you answered this question several times with the acceleration here. So I ask, planar motion requires that the velocity and the acceleration are always on the same plane, right? Now I'm replacing acceleration by the net force. This is the only change. But it's still true that here there is, somebody preferred the vector position. Remember that the vector position depends on your origin of coordinates. It's arbitrary to some extent. The velocity and the acceleration depend on the velocity, but not the origin of coordinates. So the velocity, the motion is planar given the velocity and the acceleration, right? Okay, so I'm glad I asked again the question, and I think at this point we're going to stop here, and then we are going to go through more later on. So let us go through one concept, and then we are going to start solving more problems. What are fictitious forces? Any questions so far about any of the questions that we went through? I'm going to continue repeating this one of the planar motion, because obviously this is an issue. Okay. What is a fictitious force? I told you that actually the first law, the law of inertia, tells you in which reference frames this, the laws work, right? So imagine that this is an object isolated. There are no forces acting on it. Actually, now we know that if the net force is 0, right, then the body should be moving with constant velocity. But I am accelerated, right? Assume that I am in a reference frame. I carry my reference frame with me, x, y, z, and a clock, right? I'm an observer. And I am accelerated. And I'm rushing, accelerated, right? So I see this Coke, this bottle, accelerated backwards. Are you with me? I am accelerated forward, so I see this Coke bottle accelerated backwards from my point of view. It's coming further and further apart in an accelerated fashion. Are you with me? So I say, I don't care for the first law. I want to use Newton's laws. Well, if this bottle of Coke is accelerated backwards, there must be a force, a net force pushing backwards that has to be equal to ma. So I have to invent the invisible man or the invisible woman just pushing this bottle. This is a fictitious force that I have to assume exists because I am in an accelerated reference frame. Now, that seems to be a really bad notion, to be in an accelerated reference frame. But actually, many people talk about centrifugal forces. Centrifugal force is a fictitious force. But you feel it, right? It's inertia, actually. So assume that you are in a car, right? And you're not in the driver's seat because the driver anticipates the motion of the car. But you are in the companion seat, right? And the driver turns left, right? Turns left. What is that you feel? You have experienced this. You feel pushed to the right. Steep turn, you feel pushed to the right. Why do you feel pushed to the right? You want to continue with the motion you had. This is inertia. And you need a centripetal force, because otherwise you cannot take the turn, right? If it is very violent, you are going to be, the force due to the seat is not going to be enough. You're going to be pushed against the side of the car. And I hope for your seat, your belt. So once you touch the side of the car will push you, and then you feel pushed. So you feel you're pushing against the car. Then you say, oh, there is a centrifugal force. But this is because you are in an accelerated reference frame, and you feel pushed to the right because of that. This is a fictitious force because you are applying Newton's law in a situation in which you are in an accelerated reference frame, which is the car. The car is turning. Here is maybe another way. So here, obviously the tension is provided by this string. And as you see, in order for this to move, the tension has to push towards the center, right, of this circular path, right? Are you with me? If I would release this body would tend to just go in a straight path in the moment I release it, right? Are you with me? Okay. So assume now I am a little person sitting, like you in the car, sitting on this, right? Of course, this body is at rest with respect to me because I'm moving with the body. The body is at rest. And then I see this weird situation in which the string remains horizontal for no good reason. But this is in this position, right, for me. So I have to assume that there is something pushing on the other side, as I'm doing now. I have to assume that there is a centrifugal force that is maintaining this body in equilibrium in this way. When actually what is happening is that there is a net centripetal force, right? So this is a fictitious force. Now, many times, for example, for storms or so on, people study weather from a reference frame fixed to the Earth. The Earth is rotating, is really not an inertial reference frame. And then you have, for example, the Coriolis force. The Coriolis force is just inertia and combined with the rotation of the Earth. But this is a fictitious force that you have to invent in order to explain how things move, because they are rotating, because you're in a reference frame that you are rotating. So we are not going to consider fictitious forces. So there is no centrifugal force in this course. We're going to use always inertial enough reference frames, right? Inertial enough reference frame. So this is what is explained here. There is a fictitious force that I have to find in order to apply Newton's laws. For example, here in this case, right, I would see this standing still with respect to me in this way. I will have to assume that there is a centrifugal force, the one I'm applying now, when actually there is none. It's simply that this body is rotating. So this is centrifugal force is a fictitious force, and we are not going to study fictitious forces. We are going to use always inertial enough. So the forces that we have are very simple. Always in your diagram of forces, there will be the force of gravity. And we are going to go as when we restart. So let us go to the steps that you will follow to do problems. And we are going to solve a few, and we are going to add friction to these forces. First, isolate each body you are studying. Think of either M1 plus M2, or M2 separated, or M1 separated. You can study different bodies or different parts of a body and take it to be your the thing that you're studying. Draw an arrow for each external force acting on the body, not what the body is doing to others, but what is being done to the body. For each thing that is in contact with the body, there will be a force, except for gravity. So here there is gravity, and there is the string in contact. So I will have only two forces, the force of the string and the force of gravity, right? Choose XY axis for each body. If you have several bodies, many times it's convenient to choose a different frame, XY frame, for each one of them. I will make several examples. If you know the acceleration, the direction of the acceleration of each of the bodies, it would be good if you take an axis in the direction of the acceleration. You don't need to copy, right? This is already posted in the... by the way, I'm going to start, because I was asked, posting the lectures before the classes when I finish them, which may be the night before, you know. But I may change them if if I find errors, or if I don't get to the whole content. I will cut them after the class just to indicate, to be representative of what we did in class. But except for that, you have them already posted since yesterday, actually, when I finished this. So then you write, so you choose one of the axes. Why would you choose one of the axes in the direction of the acceleration? Because then in the other axis, the acceleration is 0. And your equation simplifies, right? So simple algebra leads to less number of mistakes, right? Once you get, but then you do the equations of motion. This is the equations of motion in components, F equal ma, with the sum, where F is F net, the sum of all the forces, in components, in X and in Y, equal to M in the component of X or AY. Once you get to a number of independent equations equal to the number of unknowns, your physics problem is solved. Your algebra problem starts. So you do the algebra algebraically with symbols. Never replace 20, 30, this, that, the other. No. Find the final solution Make a box if you want, your final solution. You want a time, put t equals something. You want an acceleration, put a equals something. Only at the very end, you replace with numbers with the units. Not 33 divided by 2 by 10 squared. No. 33 meters, 10 seconds squared divided by whatever. And then check your units, right? Check your units. The usual simplifications that we are going to use for the time being is that the strings and pulleys have negligible mass. So the tension is the same, the pulleys only just, bend the direction of the tension, but the tension is the same. We are going to release some of those later on. Later on, we are going to have pulleys with mass, and they rotate and things like that. But for the time being, they are negligible mass. The strings are inextensible. So if I have two bodies accelerating and connected by a string, the string doesn't extend, and therefore the acceleration is the same, the velocity is the same of the two bodies. They are linked in that manner. And then also the bodies are particles. We're going to consider them just one particle, right? Later on we are going to see that we are considering the motion of one point, which is the center of mass of the body, right? But this is later on. So neglect the dimensions, right? And we are going to see several examples. Let us make now 10 minutes. Let us return 4 minutes or so, 3 minutes past the hour.